Okay. So, I noticed some of you were not there last time, so hopefully I will do a quick revision of what we did last time. So, we are looking at a different kind of max flow algorithm. Right? One kind of max flow algorithm which we already saw was this Ford-Fulkerson algorithm, which starts with the zero flow, and as long as there is a residual ST path, we will push more flow, stop when there is no residual ST path. This is a different kind of max flow algorithm. The same problem, you have a directed graph with ST and capacities on the edges. We want to find push maximum flow, but the algorithm is slightly different. It's called preflow push, sometimes it's called push relabel algorithm. And I'll quickly revise how far we went on this algorithm and its analysis last time. So, the central notion is what is called a preflow. What is preflow? You want we are relaxing the conservation constraint rather than wanting the flow in and out to be 0, to be equal. We want this, what we call it as an excess. We want this to be greater than or equal to 0. And you also want the capacity constraint. So, any function f on the edges that satisfy these two constraints is called the preflow. And the starting preflow is basically saturate all edges out of S. That is FSV is equal to the capacity of that edge and the F okay. So, anything which is out of S, we are going to fill its capacity. For every other edge, it's 0. And so, what is the idea? The idea is that we will always ensure that there is, so there is a notion of residual graph, the same as just like we had the residual graph for a flow, we can also define it for pre-flow, where it is on the same set of vertices and you have an edge UV. With the residual capacity as a flow, and you also have it on the reverse direction. We assume that the capacity on the reverse direction is 0, then it's 0 minus flow on that direction. So, it's okay. So, whenever you have a positive flow going in one direction, you write the reverse edge with the flow value in the residual network. So, this is exactly as we define for flow, we can define it for pre-flow. Now, so what's the idea of this pre-flow push algorithm is that I'm going to set up some more things. We will always graph, there is no ST path, okay, and we know from all the correctness of the Ford-Fulkerson algorithm that if you have a flow where there is no ST path in the residual network, you got the max flow, right? But right now we don't have a flow because of this constraint. So, but we will always maintain that in the residual network there is no ST path, and we'll do some incremental operations, and when we reach a stage where the pre-flow becomes a flow, we stop because we know that we have a max flow because there is no residual ST path. Okay. So how do we ensure this invariant that there is no ST path in the residual network? So there is another associated notion of a height of a vertex. So what is this? We have h of s is n, h of t is 0. So what is n? This is assumed, and this is the more important thing. H of uv, h of u is less than or equal to h of v plus 1 for all u v in the residual network. Okay, so somehow what is the idea again? We start with as much flow as possible from S, and then we will try and push the excesses out at vertices to some other vertice, right, eventually to T if possible. But that may not be possible because max flow may not be equal to some of these capacities. So what happens is then some of the flow is pushed back to S. Okay, and the way we are going to do this push of the excess at nodes is using this height notion, where we will push. Okay, only from a higher vertex to a lower vertex. Okay, so the height somehow indicates some sort of a slope of vertices. So we will always push from a higher vertex to a lower vertex, but for an edge to have, okay, so from this, so if uv, so if h of u is greater than h of v plus 1, this implies uv is not in the residual network. Okay, so we have this condition tells me that if h of u is strictly greater than hv plus 1, then that edge does not have a residual capacity to push anything anyway. So we will always push when h of u is equal to h of v plus 1. Okay, so so some sort of a corollary of this condition. Some other useful property which we proved right away, that there is no ST path in GF at any point as long as you have what is this preflow and this height condition satisfied. Why is this? Anybody remembers the proof? Condition that if you suppose there is an ST path in your residual network, then height of S is less than or equal to height of, let's call this V1 plus 1, which is less than or equal to height of V2 plus 1. So in particular, height of S is less than or equal to height of T plus the length of the path. My height is maintained in a way that height of S is n, height of T is 0. So I have n less than the length of the path. The length of the path is strictly greater than n, which is a contradiction. Okay, so as long as I maintain this condition on the residual network, there is no ST path in GF. Okay, so this is one of the things I said we will maintain all the time. Okay, so now what is the preflow push algorithm? Okay, so it has two operations: push on an edge UV. When is this applicable, right? I'm going to push some edge through this edge UV. I want the following conditions to satisfy. E of u must be strictly greater than 0. U should have something excess to push, right? What else do I want? UV edge should have some residual capacity. To send. Here is an important property, which is that height of u is exactly equal to height of v plus 1. If all these three conditions are satisfied, then I am going to push. So the whole algorithm is that first we start with this initial preflow. Now vertices have some excess capacity. We will try and push them out through some edges. Okay, that's the algorithm. And eventually we will stop when every excess capacity is equal to 0. So you actually have a flow. Now, but I'm going to push things very carefully, and that's where this height function is going to be used. And when do I push? When all these three conditions, that I have something excess, this edge can take something, and if height of u is equal to height of v plus 1, then how much do I push? Minimum of E of u and Cf of u. Right? This is the minimum, whatever I can push, whatever the excess capacity and whatever the edge can take, minimum of it. So this is one condition, and there is, suppose this is not possible, that what is not possible, that I have a vertex which has something excess and there are some edges which have residual capacity, but this condition is not satisfied. Okay, what does that mean? So then I will, what do? I will increase the height of u. So that I will be able to push through some edge. Okay, and that is called relabel. When is this applicable? If x's is greater than 0 and for all uv in the residual network, height of u is strictly less than or equal to height of v, then I am going to increase the height by, well, minimum of plus 1. Right. So I have this situation where there are so many edges which are in the residual network which can take my excess capacity, but their heights are either equal or less. No, sorry, their heights are either equal or more. So what do? I push this guy's height to one more than whatever is the minimum of these heights, so that I can now push through some edge. Okay, now the algorithm is, what is the initial height? Is h of s is equal to n, h of v equal to 0 for all v not in. Okay, so one quick sanity check is that this height function satisfies this condition for the initial preflow. Is that clear? What do I have to check? For every UV in a residual network, I have to make sure that height of u is less than or equal to height of v plus 1. All the heights are 0 except height of s. So the worry is that if about edges with s and something else, because height of s is n, the other guys are 0. So for such edges I need to worry about. Thankfully such edges are not in my residual network, because I have saturated those edges in my initial preflow. My initial preflow was saturate all the edges coming out of S. Okay, for all other edges it's easy to see. Okay, so now the algorithm is start with initial preflow, which is saturating all edges out of S to their capacity, and while E of V is greater than 0 for some V, apply push or relabel as applicable. Okay, so this is the algorithm. Okay, so whichever is applicable, keep applying them. And when do you stop? When all the edges have capacity 0, excess 0, all the vertices have excess 0, at which point you've got a flow, and we have always maintained the invariant that there is no ST path in GF, so we got a max flow. Okay, so now the question is, will the algorithm terminate? Will it always have something to do? Will it get stuck? These are the questions, and we addressed some of them last time. So what we addressed are, which is easy to see, that push or relabel will always be applicable. So you'll never get stuck. Right? If you have a vertex which has some excess, and if this is not satisfied, that means this. So you will find some edge to push to by increasing its height. So the only thing to look at carefully here is that, suppose I have excess, why should there be some edge out of it in the residual network at all? Okay. The way I have written the conditions, it seems obvious that if you do not have these conditions, then I will increase my height. So as long as there is some edge out of it in the residual network, I can push, right. But why should there be some edge out of a vertex which has an excess? Is that clear? That we need to check that, and why would there be such an edge? Why? Yes, exactly. So if I have a vertex which whose, then how, what does it mean? Its flow in is greater than flow out. So how is it getting its flow? Now there is some incoming edge where there is some flow is coming in. So by the definition of residual network, the reverse edge will be part of the residual network. So the set on which you are doing the minimum is not an empty set. Okay, so push relabel always applies is clear. So the algorithm will never get stuck. So only thing we need to show is that the algorithm will terminate, and the way we, and it's also clear because of this lemma that when the algorithm terminates, what we have is a max flow, because what we have is a flow because all the excesses are 0, and because of that lemma we know that we have a max flow. So we were en route to trying to show that the algorithm will actually terminate, and the way we were going to do it is by giving a running time bound and the number of pushes and number of relabel operation the algorithms will do. Okay, so we are left to just analyze the algorithm. I know whatever, how many pushes, how many relabel operations this algorithm will do. Okay, so towards that, the height of any vertex is less than or equal to at most 2n minus 1. This is something again we proved last time. And how did we prove this? Okay, let me just write sort of a single line proof. I mean, height start with 0 for everybody. Is the height of a vertex, the relabel operation. Okay, and Yes. So I think the claim, a claim which is part of the proof is that EV is greater than 0 implies there exists a V to S path in the residual network. Okay. We proved this last time, so I'm not going to repeat the proof. But essentially, what we did was, I mean, the intuition is that how did again we get excess in the flow? That's the intuition. But the way, formally, the way you prove it is by, taking V and all reachable vertex from V in the residual network, and suppose let's call this R of V, vertices reachable from V. This is the remaining vertices. Suppose S is here. We looked at the sum of the excess of these vertices and we know that it's strictly positive, which means that there is some edge which is coming from here to here on which there is a non-zero flow. So this reverse edge would appear in the residual network, which means it contradicts the fact that this is all the vertices you can reach from V. Okay, that's sort of the one line argument for it. So this means, again, because of this height condition, that you have a path from V to S. So look at that path, and height of V is less than or equal to this vertex plus 1 and so on. Finally, this is n, and height of S never changes. So this cannot be more than n plus the length of the path, height of this vertex. So which is at most 2n minus 1. So a corollary of this is the number of relabel operations is at most n into, or more precisely, because a relabel operation increases the height of a vertex, and it can't do it forever because height of a vertex cannot reach beyond 2n minus 1. So for a single vertex, it can do so many relabel operations to get it to 2n minus 1. There are n minus 2 vertices other than S and T. So the number of relabel operations is n square, okay, order n square. I think this is where we stopped last time, and we were yet to prove the number of push operations. Okay, so let's categorize the push operations into two types: saturating push and unsaturating push. Okay, you can guess what these are. Push is always through an edge. A saturating push means that it saturates that edge, that whatever you pushed is actually equal to the residual capacity. Okay, an unsaturating push means that you can push it to whatever the residual capacity. And why does that happen? Because you don't have enough excess. Your excess was smaller than what that edge can take, so you sent something through that edge, but not enough to saturate that edge. Okay, so those are the two different types of push operations. So let's bound one of them. Which one? Let's bound the saturating pushes. Okay, that's easy to do. Number of saturating pushes I'm going to say is order mn. Do I want to write more precisely? I think 2m into n, let's say. Okay, so this The argument is similar to the Edmonds-Karp algorithm, where we said number of times an edge becomes critical is at most order mn or n times. A particular edge becomes critical in an augmenting path at most n times, simply because we said you push something through that edge, and again to push something through that edge, if it is already saturated, means that you have to push something back and then send it again. So the shortest path length from S increases by at least 2, and that was the argument. Here we will use more or less the same argument. We will say that the height of a vertex will increase by at least 2, and the height is at most 2n minus 1. So an edge is involved in a saturating push at most n times. Okay, that's going to be the argument. I already said the argument. We just need to fill up the details. Why? So, okay. So the claim is an edge UV is part of a saturating push in the whole algorithm at most n times, strictly less than n, but yeah. Okay, what's the argument? Because remember, we push only if this condition is satisfied. Okay. Oh, one other thing I forgot to mention, which we again verified last time, is that after every push and relabel operation, what you have is a preflow, and what you have is a legal height function. Okay, we just need to verify this, that the push and relabel operation, what you have is a preflow is clear, because we always send by residual capacity, so we never exceed the capacity. But the height function, which this criteria is satisfied, needs some check. Okay, but can be checked, verified. Okay, so let's say you are pushing and it is a saturating push. What does that mean? That U no longer has excess after the push, right? Because, sorry, no, you can have excess. You can have excess because I push only through this. Yeah, okay. So I take back. So this is a saturating push, which means that height of U is equal to height of V plus 1, because that's when you can actually push at that time. Okay, I'm using H for height. Okay, what happens after this push? This edge UV goes out of the residual network. Okay, this is more or less the exact argument in the Edmonds-Karp shortest path. So then, how can it participate in saturate in any push at all? Well, it has to come back to the residual network, right? How will it come back to the residual network? There must have been a flow from V to U, right? How can you send a flow from V to U? This condition has to be satisfied. So height of V must be equal to height of U plus 1. So we should, at this point, height of V is actually 1 less than height of U. For a flow on the reverse, for the edge to get into the residual network, there must have been a flow through the edge VU. For a flow to happen through the edge VU, height of V must have increased by at least 2 from what it was. Okay, so between two saturating pushes, height of a vertex increases by at least 2, and height can become at most 2n. So that proves this. Okay. I didn't write all the details, but okay, for height of V should increase by at least 2. So that bounds the number of saturating pushes, right? Because I mean, if you have an edge UV, you might push through UV or push through VU. So both possibilities are there. That's why it's 2m, and the number of times the edge is part of it is at most n, so it's 2mn. Okay, so we have bounded the number of saturating pushes to. Now I have to bound the number of unsaturating pushes, and this is through an interesting, some sort of a potential argument. Okay, so now the claim is number of unsaturating pushes. I'm going to say at most yeah, okay. Right. So what we're going to do is look at this, consider at any point of time this potential which is equal to summation okay, so what is happening in an unsaturating push is that, okay, so the good thing about saturating push is an edge goes out of the residual network. What is a good thing about an unsaturating push? Excess of a vertex becomes 0. Right? I'm going to just, excess of a vertex at a height, larger height actually becomes 0. Okay, because you push always to a vertex at a lower height. Okay. I mean, excess of a vertex becomes 0, but excess of some other vertex may increase. So you can't just say that that's a progress, but the real progress is excess of a vertex at a larger height becomes 0. Okay, so that's what I'm going to take advantage of and argue here. So if I look at this, okay, this is just some function on my graph. Given my preflow and the height, I can compute the excesses, and I just sum of the height of the vertices whose excesses are strictly positive. Okay. So initial phi is 0, right? Because S is the only vertex which non-zero height, but I'm not considering that. Okay, so we and X, it has only flow going out anyway, so it doesn't have flow coming into S at this point, so it's fine. Right? And okay, what happens to an unsaturated push? We just discussed unsaturated push. I claim decreases phi by at least 1. Right? Why is this? Because an unsaturated push, why is it unsaturated? That I don't have enough excess, so I pushed whatever I could from my excess. So this guy's excess becomes 0. And the only other excess that could change is this. Maybe it was non-zero, it was 0 before, now it has become positive here. Maybe it was even positive before, I don't know. But nobody else changes anything. Their excess doesn't change. So, but we know that height of u is exactly, or height of v is height of u minus 1. So, if this vertex was not having excess and now it has got an excess, then sum would have decreased by at least 1. If it was already having an excess, then its height would decrease by height of u, because this thing is out of that sum. Decreases by at least 1. And I claim that every other operation, the saturated push and the relabel operation, actually increases phi by some small quantity. Okay, what happens to relabel? Increases phi by at most 2n minus 1, right? Because it increases the node height of some vertex, but its height can get maximum 2n minus 1. So that is the maximum increase a relabel operation can do it to phi. And saturated push or saturating push, what does it do? I claim again, well, so again it's uv, you've saturated this edge, excess of this vertex could remain. This vertex may become a vertex with the new excess now, it was not there, positive excess before, and so its height I have to add it to phi, and it can be at most 2n. Now between these three statements, our claim should follow, right? So what? So phi starts with 0, and these guys keeps increasing the phi by at most 2n. 2n is a very conservative amount. So the maximum value of phi can be the number of relabels times 2n plus the number of saturating push times 2n, right? So it's like mn square plus n cubed. That is the maximum value phi can get. So can you have, and phi remains non-negative. So you can't have too many unsaturated pushes, because phi is a value which just goes all the way. Its maximum value, its maximum value is only about n square, but number of increases, what I want to say, yeah, I mean, this is something we have seen, even in like multi-pops and push kind of argument, that a number of pops is bounded by the number of pushes. Remember, this is sort of like the first lecture we had. It is very similar to that kind of an argument, that these guys are increasing phi and unsaturated push is decreasing it, but the number of decreases cannot be more than the maximum value of phi, because otherwise it's just going to bring it down to the negative value. So you might have, so if you sort of plot how the increase and decrease happening, so you may have a relabel increasing it, a saturating push increases it, and maybe an unsaturating push decreasing it, and then increasing it, decreasing it, it goes on. But you know that the maximum value of phi is some order mn square plus n cubed, so the number of decreases, okay, so I'm just going to say hence number of unsaturated pushes is at most order mn square, because mn is the number of saturating pushes, and each push can increase the value by n plus n cubed. Since this is bounded, I'm just going to say this. Okay, we're going to again use this kind of an argument later as well, but so is this clear? Okay, so that sort of argues that the algorithm will terminate with so many pushes and relabels. Now there is one little thing about actual implementation of this algorithm, right? So how much time a relabel operation takes, how much time a saturating push takes, how much time an unsaturating push takes, and what sort of data structures you use. So I'm going to just leave this. Right, it's like in the Edmonds-Karp augmentation algorithm of Ford-Fulkerson thing. We said there will be mn many augmentations, but each augmentation takes order m time because you need to construct your residual network and find the shortest path. So you multiply by m. So similarly, all I'm saying is the number of relabel operations, push operations are bounded, but how much time does it take for each one of them? Well, if you look at locally each one of them, a push operation is actually constant time, right? Assuming the preconditions are satisfied, you just adjust the capacity of an edge, height changes something, some residual network, you may need to adjust it. Relabel operation looks at the degree of a vertex and look at, you need to check the precondition to see that for every edge going out in the residual network, the height is less than or equal to. After that, you find the minimum and then you update it. Okay. So overall, I claim that you can be implemented. So you have a list of vertices with excesses, and then slowly pick one by one and look at the residual network. You need full representation of the residual network to do all this. It can be implemented in order mn plus number of unsaturating pushes. Which means in this algorithm it will be like mn square. Okay, and what was our progression of the running time of Ford-Fulkerson algorithm? The first algorithm was something like m times f star, right? If f star is the maximum flow. Then we said, if you want to bound by something like input, if you sum the capacities of edges going out of S, call it as capital C, then that's a sort of a bound for the max flow. You can get it this much time. And I'm not sure you saw this algorithm, but there is an algorithm which actually takes m square log C, and then this was m square n was this Edmonds-Karp. And now this algorithm is m n square. Okay, so we'll do one more heuristic improvement to this, and then we will look at some couple of applications. Okay, then let me keep this. So here is so this is again very generic, like Ford-Fulkerson algorithm. You find an augmenting path, and augment is what that algorithm said. Here you find some vertex with excess and do something, right? Instead, if we find EV with the largest height, find V with the largest height such that EV is greater than 0 and apply pusher label. So initially everybody has height 0 except S. So it will be an arbitrary vertex, but as you move on, you will find a vertex with the largest height and then do this push. Move order n cubed. Okay, that's better than mn square, especially for a dense graph. Okay. Let's see a quick argument of why this is. So, is the algorithm clear? Again, we start with the initial preflow as we did, and among all vertices with excess, positive x's, you find a vertex with the largest height and apply push or relabel whatever it applies. Okay. And the argument, again, it's something like very similar kind of a potential argument. Instead of this, we will say let's look at this potential. And notice that, so let's see which operation will actually increase phi. So initial phi is 0. Which operation will actually increase this new phi, which is the maximum height out of these 3 operations? Okay, I claim that a push operation will not increase phi, regardless of what kind of a push it is. Why? Because they are always increasing from a higher vertex. So this is a max of the heights, right? So look at your network, look at all vertices with excess positive, look at the maximum height, and that's my phi, right? So if you look at a push operation, if it is a saturating push, then this edge is out of the residual network. This may become excess, but the max height will remain as this, because its excess remains as positive, or maybe it has become 0, maybe both are equal. Either case, either the max height will remain this or one less, right? Nobody else, because this is the max height. In fact, max height may be some other vertex with an excess with that same height. That's also possible, but it will not increase in any push. If it is saturating push, if it's an unsaturating push, the same thing, right? Because this edge is out of the residual network, but this guy still has an excess and its height remains the same. So it never increases. Only relabel increases phi, because prelabel's operation is to increase the height. So it might take the largest height from where you are trying to push, and push is not applicable, it might increase the height. Okay, whatever it was, right? So same kind of an argument. Oh no, okay, not same kind. Okay, a little bit slightly different. So number of changes to phi, or number of times phi changes, is, I claim, order n cubed. Very similar argument, because the number of relabel operations is n square, and each relabel operation can increase it by some n, and others are only decreasing it, so there cannot be too many decreases, too many other operations. So number of times phi would change. In the same phi, while phi remains at a particular time, n cubed or n square, I want to actually say n square. right here. I'm not talking about the value of phi, because value of phi we know is fixed. I'm saying a number of times this object phi changes, because is a relabel operation can increase it and increase it, maybe there is increase it. So, there will be n square many relabel operations, and others will come and decrease it, but I know I can't make it below 0. So, the number of times they will do it is at most number of relabel operations, which is n square. Okay. Now, I claim when phi remains a constant, number of unsaturating pushes is right. Why? Because I claim that at most one per vertex. Because you have a vertex and it's doing an unsaturating push, what happens? This guy's excess has become 0 because it's doing an unsaturated push, right? Now for it, for it to do another unsaturating or any saturating push, its excess has to become positive. For that, a flow has to come from here to here. For that, its height has to go above this, and so phi will change. Right. So, if you fix a phi, then the number of pushes, number of unsaturating pushes is at most n1 per vertex. So, I claim because n square different changes at phi, and each time I might do unsaturating pushes is n cubed. So, I mean this assumes that I am actually pushing from a higher vertex to a lower vertex, because I mean highest a vertex with the highest excess. Where am I using that? Because okay, and pushes decrease, don't increase. To claim this pushes don't increase phi, I am using the fact that I am always pushing from the highest vertex axis, right? Because suppose here is the vertex whose height is the highest, but I am pushing this, right? So I am pushing it like this, which is not the highest, and height of u, this is can push increase the height of a vertex. Increase the max height, okay. So it can make some other vertex with excess flow above the max height. Can it? No. So where am I using the fact that I am always pushing from the highest vertex? No, push condition is always when height of u is height of v plus 1, right. So when I am pushing from u to v, height of u v is height of u minus 1, okay. So this condition I am not changing. This is a pristine condition for my push operation. All I am doing is that I always pick the vertex with the highest vertex with positive x's and I'm doing the push. But suppose I do it something intermediate, is it possible that the max height increases? So otherwise, where am I using the fact that?
The number of times the potential changes.
No, I'm not really, right? So actually, I'm using it here. Okay, so to say that when I push from U to V, so max height remains at some point, okay, and I pushed U to V and I say for this vertex to participate in another push means that this guy gets an excess, need not come from V itself, right? I'm only talking about a vertex. So this vertex gets, because somebody else pushes it and it gets an excess. If it is not the highest vertex, highest height vertex, if there is somebody else whose height is higher than this, while the max height remains the same, somebody else might be pushing something to it and this guy will get an excess and it may participate again. It cannot do that because this is the one with the maximum height. Okay, this is where I am using that number of unsaturating, one per vertex, because otherwise this guy may get an excess from some other vertex and it may be again pushing through some other edge. So to argue that at most one per vertex, I need the fact that I am always pushing from the largest height vertex. Yeah, okay, good. Okay, good. So I am going to now wind up algorithms for max flow. So that means like we can improve this to n cubed, and there are even better algorithms. Okay, but there are really these two types of algorithms we have seen. One is this preflow push, and the other is Ford-Fulkerson type algorithm. Okay, now we will see maybe a couple of applications of max flow Minkowitz theorem. We have seen already quite a few. We have seen. Have we really seen for bipartite maximum matching in this class or in your previous lectures? Okay, so let's quickly do that again. And we saw that there's IPL tournament scores and the remaining matches, and to argue that whether a particular team survives, you use Maxwell-Minkowitz theorem. So let's So applications of max flow as well as max flow Minkowitz theorem. So bipartite matching. So what's the problem? You're given a bipartite graph and you want to find this is what is called a matching. Okay. So how do you apply flow to this? Well, you create two vertices S and T, make all the vertices of X adjacent to S, make these edges going in this direction. What are the capacities you want to put on the edges? 1, right? So you put a capacity of 1, and now you run a max flow, and the claim is that there exists a matching of size k if and only if the max flow in this network is of value k. Okay, how do you prove this? So if there is a matching of size k, you take those k edges and you run a flow like this, you get a flow of size k, right? The converse is where some little bit of work is required. So if you have a flow of size k, then how do you get the matching? The first thing is it possible that in your flow you have one coming in, and maybe there is a half going out here and half going out here? Technically it's possible. Nothing which tells you that you cannot, right? So how would you argue that? Yeah, so first lemma is that if capacities are integers, there exists a max flow. It's not necessarily saying every flow with integer f values. And how would you show this? Well, run your Ford-Fulkerson algorithm or Preflow push algorithms. In all these algorithms, the way we are augmenting the flow is only by integers. If the capacities are integers in the max flow algorithm, Ford-Fulkerson, we will take the residual flow, that is a critical flow, we will always augment it by integers. Same with Preflow push algorithm, right? We always take the minimum of the x's and this flow, and these are all integers. So it's an algorithmic proof that you can get the max flow with integer values. So that's one thing we can deal with. So this may be part of the max flow, but if there is such a thing, I can always obtain a max flow where all the flow values are actually 1 or 0, right? So now you pick up edges here in this part which have flow as 1. The claim is that they form a maximum matching, or they form a matching of size k, right? Why is it a matching? Because you cannot have two things coming here, because this guy's capacity is only 1, and with this lemma, only one of these edges can get a positive flow. By the same reason, since this has a capacity of 1, you can't have two edges coming into it. So what you have is a matching, and if you have a flow of size k, then you can argue, take this cut. This cut has capacity k, so that means there are k edges going from x to y. Okay, so it's obvious, but it requires some careful things, some proofs to be done. Oh, here is a more important, more interesting result, which you can use using max flow Minkowitz theorem, which is that, so suppose cardinality of x is equal to cardinality of y, and if the maximum matching is not equal to cardinality of x, then what do we know? Right. So that is, I am saying there is no perfect matching. Right. If there exists no perfect matching, then what? There exists a contained in x such that neighborhood of a cardinality is strictly less than. What theorem is this? This is called Hall's theorem, right? So it's actually known if the direction is clear, that if there is some subset for which the neighborhood is strictly less, then if you pick that subset, you don't have enough neighbors to match. So you need at least cardinality of A many neighbors. But this is the other direction, that if there is no perfect matching, then you can exhibit a set A whose neighborhood set size is strictly less. How do you prove this? There are lots of proofs. You can prove max flow, use max flow min. Okay, let's see how we would prove, right? So I run my max flow here, and let's say this is equal to n. So proof. So run max flow algorithm on my network. Call it G prime, because G prime has S and T added with capacities and so on. And we know that flow value is strictly less than n, right? Because if the flow value is equal to n, from this claim we have a matching of size n, there is a perfect matching. So flow value is strictly less than n. So there exists a cut AB such that the capacity of the cut AB is strictly less than n. Let's look at the cut and then we'll get our so let's say I'm going to use it A prime B prime. So this ST cut, right? So how does the, so here is my X, here is my Y, and here is T and S. So my A prime would pick up some vertices from X, some vertices from Y, and that's my A prime. And this is my B prime, and the cut I'm talking about is all these edges. And we know that the capacity of that cut is strictly less than n. What is our goal? The goal is to get some subset of X such that whose neighborhood is strictly less than cardinality of A. So what's a natural candidate for A? A prime intersection X, right? Yeah, but before we do that, yes, that's going to be, but let's make some observation about A prime, right? Okay, so here is an observation. X is in A prime implies I'm going to put all its neighbors also in A prime. Or what I mean is that there exists a min cut with such a property. Remember, we went through a very similar argument in that IPL tournament scoring thing, where less we got a cut, and we had to find a subset of teams that satisfy some condition. We needed to prove some little observation, move things around a little bit, and then we used the cut value strictly less than and proved it. So something similar to that. Okay, so why is there such a cut? Because if I have an X here, and if its neighbor Y is sitting here in B prime, then what happens if I pull all Y into A prime? What happens to the cut value, right? So there will be an edge from Y to T, right? This edge is not part of the cut now, but when I pull Y there, it will become part of the cut. So the cut value will. This edge, which is part of the cut, will not be part of the cut, so it will decrease. Okay, and in fact, there may be, for Y, there may be several edges which are coming in, and all those cut value will claim that by pulling y into x, the cut value either remains the same or it decreases. And no, and there may be yes, and there may be edges like this, okay, which is not part of the cut now, but when I pull y in here, will it become part of the cut? No, because I care only about edges coming from that side to this side. Remember, it's a directed graph. So I care only about the edges coming in this direction. These edges will not become part of the cut again. So this claim can be ensured by moving the neighbors into A prime. So now the claim is A prime intersection X, let's call it A, and I want to show that A has the property that its neighborhood is strictly less than A. Okay. Then why? Let's see what is the cut capacity of the cut A prime B prime. Well, from S there is edges to x minus A, so it's cardinality of x minus A, right? If you look x minus A prime or A, doesn't matter. Yeah, x minus A. So this is my A. So x minus A, so these are the vertices and S has edges coming in, these are all part of the cut, plus what are the edges in the cut for all the vertices here to T, right. So plus I am going to say y intersection B prime, this is the value of the cut. X minus A, S has edges to, and edges from here to here, because anything from here there are no edges because I pulled all the neighbors out there in there. So this is my value of the cut. So this is equal to n minus cardinality of A. So this is strictly less than n plus cardinality of y intersection B prime. This is greater than or equal to n minus cardinality of A, but who is here? Definitely the neighbors of A are here, and maybe more, because I pulled all the neighbors into, so it's now n cancels, and what you get is neighborhood of A is strictly less than cardinality. Okay, so not only you can use to find the maximum matching, I mean in fact there is a version of a perfect matching. You can also come up with a witness set if the perfect matching doesn't exist. So that's the nice duality about Max-Flow-Minkert theorem. Right? If the max flow value is less than that, then you can give a cut which matches that cut capacity is equal to the flow. So this is maximum number of edge disjoint ST paths. So given a directed graph with some special nodes S and T, and say I am interested in maximum number of edge disjoint ST paths in the graph. Okay. some directed network is given. There is some two vertices S and T, and I'm interested in maximum number of edge disjoint ST paths. Okay, these paths can intersect at some vertices, but no two paths can share the same edge. Okay. Okay, this is already in the form of a max flow input where you have an S and a T and a directed graph. You just have to make it into a network. A natural thing is to put some capacities as 1, right? The claim is that max flow value here is K if and only if there exists K edge disjoint ST paths. Again, one direction is easy, that if you have edge disjoint ST paths, then you just send a flow of 1 through those edges and you'll get a flow of K. Now the converse direction, if you have a flow of K, because of these integral capacities, we can assume the flow values are all 0 or 1. Now you have to extract out a different ST paths. Okay, so I'll just leave this as it's again very intuitive, but a formal proof. You just have to argue that you can just sort of pull out a path, ST path from each flow. So you start with S. Suppose the flow value is strictly greater than 0. There is some edge with a non-zero flow. Well, because of the integrality condition, the flow value is 1. Because of the conservation, that has to go somewhere. Keep following it up. Either you will reach T, then you got an ST path. You can reduce the flow on these edges, apply induction. Now you have a 1 less flow. Or what can happen is that you will get into a cycle. What do you do in this case? You applied flow algorithm, you got a flow of size K. Now I'm following through the flow. So here is a flow, an edge with non-zero flow, and follow, and if it reaches T, great, I got an ST path. But if it comes back and goes here, then basically you just decrease the flow out of this cycle, right? Make this 0, 0, 0, 0, and because this 1 and this 1, so there must be something else going out, take that. So nullify this cycle, follow through, and or you can apply induction again, because number of edges with non-zero flow has come down now. The flow value has not come down. You will apply. Okay, so that's sort of the proof. And the duality theorem here is maximum number of edge disjoint ST paths is equal to minimum number of edges whose removal disconnects S and T. Okay. So this is actually called Menger's theorem. You can prove this using Max-Flow-Menkat theorem. You can also prove this for undirected graph. more or less everything goes through. So what do? You make, I mean, network flow requires a directed graph. So what do? You make edges in both directions and run your max flow. So if there is k edge disjoint ST paths in your undirected graph, that will correspond to a flow of value k. The converse direction requires a little bit of work. I mean, you can apply this induction basically, but what could happen is that these guys are edge disjoint in the directed sense, but in the undirected sense it may not be, because one of the directed path may use this edge, another directed path may use this edge, but in the undirected sense it's the same edge. But when would this happen? Because you extract this out from the edges which have non-zero flow. So when would you have a flow of one here and a flow of one here on both directions? Well, you could have, but you can sort of get rid of this. It's like how you got rid of a cycle. Okay, you can get rid of it, and okay, the same. Needs a bit of careful things, but so in a sense, this Menger's theorem is a sort of a special case of max flow Minkert theorem. Max flow Minkert theorem is for arbitrary capacities, but here you can think of it as where capacities are one. So, okay, so we have seen the max flow algorithm and a few applications of max flow, and the Kleinberg-Tardas book has quite a few applications. Some on the graphs, but some they don't even look like a graph problem, like the score thing which we saw. Or yeah. Okay, stop. I sort of rushed through towards the end, but I think the arguments are clear and the details are in the Kleinberg-Tardas book.